So, hello everyone. Today we will discuss the effect of self-assembled monolayers on biointerfacial interactions. So, basically we will see how a surface can be modified and how it tunes the biointerfacial interactions. So, in the last lecture we discussed about the self-assembled monolayers, how it is defined and how it is formed. Then what are different types of self-assembled monolayers, starting with monosams and the mixed sams, and what kind of interaction between the surface and the surface modifying agent take place, and what are different techniques to form the self-assembled monolayers. And after that we discussed the kinetics, how we can analyze the kinetics of SAM formation. So, today we will see two cases where self-assembled monolayers have been applied on a biomedically relevant titanium surface, and after the modification we will see how this biointerfacial interactions improves. So, the first one will discuss the surface functionalization of titania by formation of different self-assembled monolayers to see how it improves the protein adsorption and the fibroblast cell adhesion. So, the very first step will be the surface modification of titania and its characterization, then protein adsorption. So, here we have chosen two protein, albumin which is a non-adhesive protein and fibronectin which is a adhesive protein. And then after that we will analyze the adhesion of fibroblast cells on the modified surface. So, this is published in Langmuir. So, for more detail you can refer this paper. So, why to choose titania? Because titania and its alloy are widely used as a implant biomaterials, particularly in orthopedic and dental applications, because of its excellent mechanical properties like low elastic modulus, good fatigue strength, but as a material it lacks in osseointegration and osteoconductivity. So, how to improve this cell surface interactions? One way to apply a different coating or modify the surface. So, the surface modification improves its physicochemical as well as the biological interactions at biointerface. So, in this work we have modified the titania surface using different self-assembled monolayers of amine group, octyl group, mixed of amine and octyl, also the one hybrid SAM and carboxyl SAM. So, we have formed the different self-assembled monolayers to tune, or you can see the design the surface with a wide range of wettability and analyze how it improves the protein surface as well as the cell surface interactions. So, here this is if you remember the last lecture we have already discussed this. So, this is a titanium oxide surface. If you hydrolyze, it will have the OH group, and this OH group can react with the head group of the surface modifying agent, and in this way this surface modifying agent is covalently attached on the surface. So, here we have prepared a monosam of amine group. So, X will be NH2, or octyl group the X will be the CH3, and from the CH3 group if you simply oxidize it, then we will form the COH group. So, we had three monosams, amine, octyl as well as the carboxylic. Now we have also prepared a mixed SAM, where in case of mixed SAM both the amine as well as the octyl group in the solution. So, we will have both amine and octyl group on the surface, and in case of hybrid SAM the amine SAM was first formed, then it was reacted with the para-toluyl isocyanate, which ended up with the urea linkage NHCONH. So, the same SAM molecule is now having a hydrophobic group as well as the hydrophilic group. So, both functional groups are present in the same chain, that is why it is called the hybrid SAM. So, these were the different type of SAM which were applied on the titania surface: the mono SAMs, amine, octyl and carboxylic; mixed SAM, mixture of amine and octyl; and hybrid SAM. So, this is the surface wettability and surface energy of modified surface. So, for the blank or the hydrolyzed or clean surface, contact angle was 30, it was found to be the hydrophilic, and for amine 63, octyl 105. For the mixed, it is coming in between amine and octyl 86. Hybrid, as expected, it is having both hydrophilic and hydrophobic moieties. So, it is also having a moderate wettable 82 degree, and COH again it is a hydrophilic surface. So, if you want to calculate the surface energy, we have to measure the contact angle using two liquids. The one was the water, other was diiodomethane, and based on that we have calculated the surface energy using geometric mean method. So, here the least surface energy is coming for the octyl, and the maximum surface energy is coming for the blank surface followed by this COOH surface. Now, here we have also performed the adsorption of a protein fibronectin. So, after the adsorption of this particular protein, there is a, you just compare these two values, this one and this one, there is change in the surface wettability again. So, what it says is, depending on the surface wettability, a protein molecule reorient itself in a different manner. So, that is why even after the adsorption of protein, all surfaces are not having the same contact angle or same wettability. So, they are having the different wettability, and for the mixed and hybrid surface, the contact angle before modification was 80 plus, and after the modification it is around 52. So, similarly, after the protein adsorption also we can calculate the surface energy, and it was calculated by measuring the contact angle of water and diiodomethane, and you just see there is again change in the surface energy after the protein adsorption. So, for the hydrophilic surface there is a slightly, here there is a decrease in the surface energy after adsorption, here again there is a decrease in the surface energy after adsorption, but in case of hydrophobic surface or moderate hydrophobic surface there is a increase in the surface energy after the adsorption. And also, as we discussed in the last lecture, by modifying or forming different SAM, we should be able to tune the surface roughness at the scale which matches with the length of that sealant molecule or length of that surface modifying agent. So, as you see, the blank surface itself was the micro rough. So, but still there is some change because of the due to the presence of the surface modifying agent on the surface. So, here is the protein adsorption. So, as we have seen, the different surfaces have different wettability, and so we use two proteins, albumin as well as the fibronectin. So, in case of albumin, if you see the blue point, with increase in the surface wettability, we can see a sort of increase in the protein adsorption. So, typically this albumin is considered to be a hydrophilic protein, and if you are increasing the surface hydrophobicity, there is a increase in the protein adsorption. But if you see the trend of fibronectin here, you observe a decrease in the protein adsorption. So, what it suggests, the fibronectin is a hydrophobic protein. So, its orientation or it orients on the surface through hydrophobic patches. It means on the hydrophobic surface this is less adsorption, and hydrophilic surface there is a higher adsorption. So, what it suggests is the thumb rule of protein adsorption does not apply here. So, the protein adsorption is depending on the hydrophobicity of both surface and proteins. So, we observe two different trends. In case of albumin, we observe increase in the adsorb amount with increase in the surface hydrophobicity, but in case of fibronectin, we observe a reverse trend. Now, after the adsorption of the protein, we can analyze the change in the secondary structure by using the FTIR. So, as we have discussed in case of protein surface interactions. So, here is the secondary structure. We are only presenting the, because fibronectin is rich in the beta sheet. So, it contains about more than 50% of the beta sheet, about 20% the beta turn, and then around 15% of the random. So, what is happening after the adsorption on different surfaces? You can see this is the blank surface, then this is COH, this is amine surface, hybrid surface, mixed surface, and the octyl surface. So, on different surfaces after the adsorption, the protein is having different secondary structure. If you see, these surfaces are organized with increase in the hydrophobicity, starting with the blank surface, then COH, then amine, then hybrid surface, mixed surface, and the octyl surface. So, particularly this is interesting to see in case of beta turn is increasing with increase in the surface hydrophobicity. So, we will try to relate this particular trend in terms of cell adhesion, because this fibronectin is a cell adhesive protein and it has the RGD motif which are present in the beta turn. If it means if there is a more beta turn, it means the RGD loops or RGD domains are more exposed, which should facilitate the better cell surface interactions. So, we have used the fibroblast cell for cell adhesion studies, and here this is the percentage of cell adhered and this is the cell circularity. So, detail of the cell surface interaction we have already discussed in the previous lectures, how to analyze and how this cell surface interaction studies are performed. So, here we are directly talking in terms of surface wettability. So, here we use the two kind of surfaces. The one was the cells without fibronectin and cells with fibronectin. It means in one case the surface were pre-adsorbed with fibronectin, then cell adhesion was performed. So, that is these are the filled one, and the blank circle and blank square suggests that these studies were performed with modified surface without pre-adsorbed protein or pre-adsorbed fibronectin. So, as expected, in terms of percentage cell adhered, as if it is the pre-adsorbed protein fibronectin, which is the cell adhesive protein. So, if you compare these 2 points, it is always there is an increase in the cell adhered. So, what it suggests, the surface with pre-adsorbed FN showed better cell adhesion, so as expected also. Now, if I see the maximum cell adhered was or maximum adhesion was observed on the hybrid surface here. So, hybrid surface is expected to be a potential biomaterial, because it is facilitating the maximum adhesion of osteoblast cells. Now, the similar observation was made for the circularity, means if there is a more adhesion means there should be decrease in the circularity. So, everywhere if we just compare for all the surfaces, these filled squares are having lesser values of circularity. It means they are more spreaded, cells are more spreaded on the surface with pre-adsorbed fibronectin. It means it is facilitating the cell adhesion and its spreading. So, here we are trying to correlate the change in the adhered cells and the delta beta turn. Delta beta turn means change in the beta turn after the adsorption, and here we are plotting the change in the percentage adhered delta n versus delta beta turn, and if you just see, we observe a very much linear fit. So, what it suggests is this RGD motifs is located in the beta turn, and with the increase in the delta beta turn, there is an increase in the delta n. So, this gives the insights that how pre-adsorbed protein will be helpful for the cell adhesion. Also, from the change in the secondary structure, we should be able to analyze or understand how it is going to affect the cell surface interactions. Now, we have plotted the effect of surface energy. So, here you just see this with increase in the surface energy here, this is the percentage cell adhered. With increase in the surface energy, there is increase in the percentage cell adhered. Now, there are two cases again we are discussing, without pre-adsorbed fibronectin, and the circle is the with pre-adsorbed fibronectin. So, here you just see here the surface energy is now different after the adsorption and before the adsorption, as we have seen in the previous last slide, that after the adsorption also we have analyzed the surface energy, and before adsorption also we analyzed the surface energy. So, as we observed the highest percentage of cell adhered on the hybrid surface, so we are observing the same phenomena here. But if you compare these two here, hybrid surface and the mixed surface, both are having the more or less same value of the surface energy here, but still as compared to this mixed as well as the hybrid surface is having the better cell adhesion. So, what it suggests is, apart from the surface wettability or the surface energy, the orientation or the rearrangement of the same molecules is also going to affect the performance in terms of cell surface and protein surface interactions. So, here it says we should be able to relate the surface energy with the percentage of adhered cells. So, here we are getting the least adhesion on the surface with the lowest surface energy, and maximum we are observing on the surface with the moderate surface energy, particularly this hybrid surface. Apart from this, we try to see the adhesion of bacteria. So, we have used two bacteria, E. coli and A. aureus. Particularly this adhesion of bacteria leads to the infection and biofilm formation. So, we try to see on different surface wettability how this bacteria adhesion changes, and what it was observed that the effect of surface hydrophobicity as well as the effect of surface charge both played a key role here. So, if I compare blank, COH and octyl, so octyl was having more number of bacterial cells, means this is the effect of surface energy, or you can say the hydrophobicity, but now you just see here COH is the negatively charged. So, it is not favoring the adhesion, but at the same time amine is the positively charged, and we observe the maximum adhesion of both the bacteria on the amine surface. Then it is further, so it looks like it is following a trend something like this, going to plateau, then again it is decreasing like this. So, in this way we can analyze the effect of surface hydrophobicity, effect of surface energy on the protein adsorption, cell adhesion as well as the bacteria adhesion. So, here what it suggests is this, depending on the surface hydrophobicity, we are going to observe the different amount of adsorbed protein as well as its different conformation, means different secondary structure of the adsorbed protein, and this adsorbed protein is going to have the different this cell adhesion molecules, and depending on their secondary structure after the adsorption, it is going to facilitate the cell adhesion. So, especially we observe in case of hybrid surface with the moderate wettability, we observe the better cell adhesion. It suggests that if you apply the surface engineering which will regulate the biointerfacial interactions, both the protein surface and cell surface interaction, and thus it can tune the performance of biomaterials, or it can be applied to design the biocompatible surfaces. So, now next application we will see here again the titania surface was modified only by the hybrid SAM, as we saw in the last application that hybrid SAM was found to be potential surface modifier for biomaterials. So, here the titania surface was modified by hybrid SAM, and its effect on the another cell adhesive protein collagen was used to see the osteoblast cell adhesion, and also we have seen the one cell adhesive molecule integrin expression. So, titania surface was modified by forming the hybrid self assembled monolayers. Then we used the collagen for the protein adsorption, then osteoblast cell for the cell adhesion, and then also we have analyzed the expression of a cell adhesive molecule integrin. So, this is published in Applied Surface Science. For more detail, this article can be referred. So, here this is the adsorption, protein adsorption and the change in the secondary structure. So, here what we are seeing is with time there is a increase in the amount of collagen adsorbed, and it was found that it is increasing and reaching to saturation in about 60 minutes, and here we are analyzing change in the secondary structure, this alpha helix, beta sheet, beta turn, triple helix and random. So, again for the secondary structure we have used the FTIR to analyze the change in the secondary structure. So, here what we are seeing is particularly after the adsorption there is a change in the, there is difference in the secondary structure as compared to the native collagen, but still on the hybrid surface if you just see the significant difference is not observed. It means this hybrid surface is promoting the cell protein adsorption, but at the same time without much altering the secondary structure of that particular protein. So, here this is the surface energy. So, what is happening here, with time there is an increase in the protein adsorption, means after the adsorption if you measure the contact angle. So, this is also going to change. Contact angle will also keep on increasing and this will reach to plateau like this. So, from contact angle one can also calculate the surface energy. So, why this contact angle is changing? Because of the this contact angle is changing because of the presence of the protein molecules. So, what the protein molecules is doing, basically it is altering the surface energy or the interfacial energy. So, here if you measure the contact angle of two different liquids, we can calculate the surface energy. So, we have calculated the surface energy and adsorb mass. So, it is very much following the as expected a linear trend. Now, from here one can also theoretically estimate the surface excess or the adsorb mass using the Gibbs adsorption isotherm, which says the surface excess is related to the change in the interfacial tension at ith interface, means it may be the solid liquid, it may be the solid vapor, it may be the liquid vapor, and LNC, that is the concentration, what is the temperature, and R is the gas constant. So, from using this expression we calculated the this concentration of the protein was known, at which concentration the experiments were performed. This interfacial tension was measured from this contact angle data as we discussed in the last slide. So, the surface excess was calculated. So, this is the y axis is the predicted one and x axis is the experimental. So, again you see you are observing a very much linear trend. So, it says that change in the surface energy or interfacial energy is related to the protein adsorption, and the protein adsorption or surface excess can be predicted by measuring the contact angle or surface energy. So, here is the adhesion of Mg63 cells. So, the first is saying again with increase in the time as expected, the number of cell is increasing, and here we form the three cases. One case was hybrid surface with pre-adsorbed with the collagen. Second case, hybrid surface and media was containing the FBS, fetal bovine serum, that is a protein supplemented in the media for during the cell culture experiment, and the blue diamond indicates the hybrid surface where the media was not having the FBS. So, as expected, if there is no protein, it means cell have to secrete the protein for the cell adhesion. In that case, we observed very poor cell adhesion, where media was having no FBS or no protein. Now, there are two cases. In one case, the media was having FBS, then we observe a better cell adhesion as compared to the media without FBS. Now, in the third case, when surface were pre-adsorbed with the collagen, and again the media was not having any FBS, but still we observe the better performance. So, it says that if you are having the surface with pre-adsorbed adhesive protein, in that case during the cell culture experiment, that FBS may not require, and still we can get the better, or you can say, if you just see here, the comparable amount of cell adhesion. So, now this cell adhesion, number of cell can be analyzed in terms of cell area. So, this is the cell area, it is again increasing, and maximum is observed when surface was pre-adsorbed with collagen without FBS in media. This is the average nuclei area, again maximum for the hybrid surface pre-adsorbed with collagen. And if you just see the cell shape index or cell circularity, that was the least on the hybrid surface pre-adsorbed with collagen. So, it says that if you are having the pre-adsorbed protein, particularly the adhesive protein, so they are having the cell adhesive molecules, particularly here this integrin mediated cell binding is improving the cell adhesion behavior. So, we analyze the integrin expression and just see how it changes. We analyze the three integrins, alpha 1, alpha 2 and alpha 3. If you remember, a integrin is a heterodimer and it has 18 sub units, or you can say 18 different types of integrins are available. So, we have analyzed this alpha 1, alpha 2 and alpha 3, and this is the alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha V, beta 3. So, all alpha integrins were analyzed here. So, these are the cases. This blank media was without FBS, media was with FBS, then hybrid surface, media without FBS, media with FBS, then hybrid surface with pre-adsorbed with collagen, media without FBS, media with FBS, right. So, what we are observing here is, whenever we are seeing this hybrid surface pre-adsorbed with collagen as compared with the hybrid surface when cells were incubated with the FBS in the media. So, you just see the expression of alpha 1, alpha 2 is much more improved. So, it says that this pre-adsorbed protein is having much more improved cell surface interaction through the presence of integrin molecules, which will improve the cell signaling or the cell surface interactions. Again, if you just see here, in all three cases, when the media was without FBS and when media was with FBS, there is a slightly improvement in the cell adhesion or the integrin expression. So, what it says is, if you analyze, one can relate the cell adhesion behavior with the integrin expression, because it is expected the cell adhesion is mediated by the cell adhesive molecules like integrins. So, here we have analyzed this alpha 1, alpha 2 and alpha 3 integrins with the, for all three cases, this without FBS, with FBS and surface with pre-adsorbed collagen. and what we are observing here is this is the alpha 1 is increasing, this alpha 2 is also increasing, and while alpha 3 is decreasing. So, but what we have observed is in case of pre-adsorbed collagen we had the maximum number of adhered cells, maximum number of average cell area and maximum nuclei area. So, what it says is the integrin expression is increasing, particularly this alpha 1 and alpha 2. So, better expression of this alpha 1 and alpha 2 integrins suggests the better cell adhesion. So, what we observed from here is if you are having surface with pre-adsorbed adhesive protein and here collagen 1, then it is having or it is facilitating the integrin mediated cell adhesion, which is ending up with maximum number of adhered cells, least cell circularity, better cell surface, or you can say the better average area of the adhered cells, better average nuclei size or nuclei area. So, what it says is you are having a implant surface, we can this modify by salinization, then we can have the adsorption of the adhesive protein. Here we use the collagen. Now, because of this moderate hydrophilic surface on the same, we observed very much similar secondary structure of the native and the adsorbed protein, and again it resulted the improved cellular adhesion or improved cell adhesion, and cell adhesion was mediated with the in particularly the expression of the alpha 1 and alpha 2 integrins. So, in this way this biointerfacial interactions can be tuned by the surface engineering. So, here I conclude this lecture. So, particularly in this course, this biointerface engineering, we had this 8 modules or you can say 8 weeks. So, we discuss different intermolecular forces, what is the classification of the intermolecular forces, how we can estimate what are the different functions of various intermolecular forces. Then we see what is the surface tension and what is the surface energy, how the wetting takes place, and what is the adhesion and what is the cohesion in the second module. Then we in the third module we discuss the characterization of interface, particularly the surface tension of the liquid, then measurement of contact angle, then surface tension of solids. Followed by that we discuss protein surface interactions, the basic of protein, particularly its secondary structure, its starting basic unit amino acids. Then during the adsorption what happens, what are different intermolecular forces involved during the protein adsorption, and how to quantify or analyze the adsorbed amount of the protein. Then also we discuss the kinetics of the protein adsorption. Followed by that we also discuss the aggregation of the protein, what is its kinetics of protein aggregation, and we discuss the effect of surfaces on the aggregation of protein, because the aggregation starts with the adsorption of protein. Then the next in the 6th week, 6th module, we discuss the cell surface interactions. So, first we discuss about the host cell response, then we discuss how we study the kinetics of cell adhesion or cell surface interaction experimentally, then we discuss the biocompatibility of biomaterials. Then in the last 2 modules we discuss what is the surface modification, what is the objective of surface modification, what are the different physical and chemical methods for the surface modification. Then we discuss the one case study of the physical method where calcium hydroxyapatite was applied on a titanium surface by physical methods, particularly this laser cladding and RF sputtering and its impact on the biointerfacial interactions. Then in last module we see how we can characterize the surfaces, what are different spectroscopic and microscopic methods to characterize the surfaces. Then here we included or we discuss in detail a chemical method of surface modification, these self assembled monolayers, and then what is its impact of this effect of self assembled monolayers towards the biointerfacial interaction. So, we discussed two case studies in this lecture. So, basically in the biointerfacial interactions, it is present whenever a surface comes into contact of a biological systems or body fluid. So, it starts with the first the intermolecular forces, intermolecular interactions, then surface biomacromolecular interactions, particularly depending on the diffusivity. First will be the protein surface interaction, followed by the cell surface interaction, and these interactions ultimately decides the biocompatibility or the intended function of a biomaterial. So, in this course I think we have understood the insights of biointerfacial interactions, how it takes place during the application of a biomaterial, and if you want to improve or tune those biointerfacial interactions, then we can apply the biointerfacial engineering on biomaterials to design the biocompatible surfaces, to design the let us say antiviral coating, to improve the potential of a scaffold or the drug delivery system or a biosensor. So, whenever there is a interaction with the biological systems with the surface of a biomaterial, that can be tuned by biointerfacial engineering, and so this particular aspect have a lot of potential in different domains. So, thank you, and thank you for attending this course Biointerfacial Engineering. I hope you enjoyed learning this course, and I would like to thank this NPTEL head and their entire team, this head CET IIT Guwahati and the entire team, and also I would like to thank the TAs for their quality work. Thank you everyone for attending this lecture, and I also welcome any suggestion on this course. Thank you.